So much, Bob. I'm really happy to be here. I love sharing fractals with people. I just absolutely love this job. If we can get the lights dimmed up here. So I am an interesting combination of career paths, and I took a chaotic journey to get here, to say the least. So my professional training in science is in neuroscience. So I've spent a long time studying how the brain works and learning about chaos theory as it applies to brain physiology. And I did that for a bunch of years and got distracted by art. Okay, so I ended up learning a lot of things in graduate school. One of the things I learned how to do was how to make tie-dyes. It was kind of unpredictable. And I really got taken by this art form, and I started making these big tapestries, bigger and complex symmetries and connected spiral patterns. And I'm going to talk about spiral fractals tonight as one example of fractals, both in nature and in mathematics. But I started to love this art form, and I had this brainstorm one night back about 15 years ago now, and I thought, oh my gosh, I could tie-dye a hot air balloon. And so I did, and while I was writing my thesis. And then when I graduated, I had the choice of, do I go off and do a postdoc in neurophysiology, or do I go off and do an apprenticeship with a balloon builder and learn how to fly? And so that's what I did, and that's what brought me back to New Mexico, which is the world's capital of ballooning. So I live in Albuquerque now, and which is where I grew up. So I've always loved ballooning. But now I have been an artist for a number of years professionally. I've made much more money as an artist than I ever have as a scientist, which is kind of peculiar. But I'm still, of course, a scientist, and I love science. And I find that I make the best impact, or the biggest impact, as an educator. So when I was publishing scientific papers, it was great. I was doing cutting-edge research, discovering things nobody else had ever known before. And I'd publish them, and maybe 10 people would read them in the whole world. And that's a little frustrating. So what I'm doing now is teaching science, and I'm making artworks that when I fly at Balloon Fiesta, 100,000 people can see my art at a time and appreciate it without having a half-hour lecture beforehand explaining what it's all about, and so on. But I will show you some pictures of those kinds of things and ideas. But that's just sort of a chaotic preamble to explain who I am and how I got here. And my love of fractals comes about because they live at the intersection of science and art. Okay? And they are a brand new, exciting form of mathematics. I like to say that fractals are the language of nature. And we find fractals all over the natural world. And I will show you a bunch of those as soon as I get the projector a little bit straighter. But the really exciting fractals from an artistic standpoint that I'm going to show you are the mathematical ones. And so normally when I give this talk in schools, which I do a lot, I do it in a different order. And I start off with the science and the nature and all of that. But now I'm actually going to start off with the mathematical fractals because I titled this talk Zooming to Infinity. And so I really want to jump right in to infinity and show you the exquisite beauty of mathematics. Okay, so when I went to school, and probably when most of you went to school and learned math, or in particular algebra, you probably didn't think about it as something exciting and beautiful. At least I didn't. But fractals provide a context in which to really appreciate the beauty of mathematics. Okay, so here is a very interesting object. This is known as the Mandelbrot set. Some of you probably already recognize this object. It's starting to make its way into popular culture. It is the reflection of a very simple nonlinear equation. And I promise I will explain how this all works in a moment. But first, let's just experience it by zooming into it. And this is where computers provide a breakthrough, a real revolution in how we relate to mathematics. And this is totally interactive. It's being generated in real time. I've been waiting for many, many, many years for computers to be fast enough to create fractals in real time like this. And we can navigate anywhere we want to go. And kids, as young as kindergartners, relate to this like a video game. Okay, this is not an algebra lesson. This is really, really fun. But of course, it is algebra. And kids are naturally curious. And they want to learn how this thing works. Okay, so what we're seeing here is an illustration of self-similarity. That's a basic principle of fractals. Quick question, a poll of the audience. Has anybody here not heard of fractals? Does anybody not know about fractals? Don't be shy. Don't be, it's like everybody knows what fractals are. Okay, great, super. All right, well, let me just step back a moment and say what a fractal is. A fractal is a never-ending pattern.
Thank you.
Okay, a fractal is just a pattern that is made up of little copies of itself, basically, that occurs at different scales. Okay, so that's what we've seen here. This object, thanks for your courage.
It was
Thanks, Claudia, yes.
In some ways, it's sort of like what you would see on psychotropic drugs without taking them.
Well, it is math made psychedelic, yes. It's incredibly interesting and beautiful, and that's a fair explanation, yeah. Now, some fractals are perfectly self-similar, which means the deeper we go, we just find the same copies of the same thing. The Mandelbrot set is actually more than that. It is not perfectly self-similar. It actually gets more interesting and complex the deeper we go. So I'm just going to take us on a few little journeys into this to see what it's made of. And here we can see this object is made up of a whole bunch of little copies of itself. I'm going to speed up a little bit because we've got a lot of places to explore. This, of course, is made up of an infinite number of copies of itself, and so on, and so on. Now, it never ends, okay? It goes on forever. The mathematics is infinite. But the computer has certain limitations. The computer lives in the real world, and it can only calculate, this program can only calculate numbers that are 16 digits long, okay? So what that means is that we eventually hit the bottom, and we've just got there. This is what it looks like in the program. It just refuses to go deeper. So we've hit the wall for this program, but it's important to emphasize that the mathematics goes on much, much, much deeper, and there are other programs we can use to explore in greater detail further down. But as you go deeper, the numbers get longer, and it becomes much slower to calculate. So I generally like to stop around here just for reasons of convenience. Now, to put this in context, 10 to the minus 16th power, that's where we are. That's 10 quadrillion-fold magnification. Okay, if this were a real object that we were looking at, from where we started, this object now would be smaller than a single atom. In fact, it would be 1,000,000 times the diameter of an atom. Okay, an atom is about 10 to the minus 10th meters. This is 10 to the minus 16, or 1,000,000 times smaller. So very, very tiny. But of course, we're just scratching the surface, and it keeps on generating these little objects. Now try to remember how tiny that is as we zoom out. Just an exercise in stretching your brains. So I'm going to zoom on out. And it's a really brilliant illustration of self-similarity, this repetition of patterns at different scales. Okay, so here we are back at one level. And here we are in the valley that has come to be known as the Seahorse Valley. One of the amazing things about the Mandelbrot set, here we are back at the top. Okay, the converse, the flip side kind of way of looking at the scale of this thing is if this object keeps expanding as we're zooming in, when we got to the bottom there, this original object would have grown to be about the entire diameter of our solar system, out to the extent of Pluto, which isn't even a planet anymore. So very, very, very big, except in New Mexico sometimes, right? So let's go take another journey into this object, and I'll show you some more places and more features, because everywhere we go, we'll find different patterns. So it's not totally identical. And one of the great joys of this thing is that we can never run out of new places to discover. And there are many, many, many interesting things that evoke patterns in nature. So although this is totally abstract mathematical creation, wow, and look what we find here. Right. So you recognize this, I hope. And we could cycle the colors to make it extra psychotropic if you choose. Really, it's actually informationally relevant. It lets you see more detail down at the bottom when you're cycling the colors, so you can really, and I'll explain what the colors mean. It's not just gratuitous art. It is actually informational. But what we're seeing here is a little replica, of course, of the entire object, recapitulated. And we could, if we wanted to, explore the edge of this and just go down there. Now, when you do this, it takes extra patience because it gets really thick, and it's slow and hard for the computer to do it. So even though this is a state-of-the-art, super-fast computer, Fractals will always push the limits of our hardware. I'm always eager to get the next fastest computer, and I'll always wait weeks and weeks for my deep fractal zooms to render. It doesn't matter how fast the machines are. I'll keep pushing beyond that limit. So let me zoom out and show you a couple of other places. This is called the Fungus Valley, because those little things look like mushrooms. So it's really interesting how we find things that remind us of patterns in nature. And yet we're looking at a purely abstract mathematical construct. But here we find totally different appearances, different structures. But if we zoom into the middle points, the connector points, we find what's called bifurcation, where it branches and branches again and doubles and doubles. And look what we find. So indeed, we are zooming into infinity. This is an extraordinary activity. I've spent countless hours exploring this object, and I've just barely scratched the surface. Really, I could spend my entire life exploring this and still find new, delightful, beautiful places. So I'm only going to show a few more different zooms into different places before going and explaining how this works, how this relates to mathematics. I promise this is just an algebraic equation. And then I want to put it in the bigger context of why we care about these things and relate it to the natural world. And so I have all sorts of examples of fractals in nature to show you. If we just pause here at this point, you can see there's lots and lots of replicas, little guys here. And in fact, it turns out that there is nothing but little copies of this. In fact, everywhere you go, you'll either fall out of the set, the Mandelbrot set, or you'll encounter one of these objects. So it's made up of an infinite number of copies of itself and nothing else. All the stuff that you see, these filaments and tendrils, are somewhat artificial because if you zoom into them enough, and let's just pick a different one, zoom in over here. If we take a place like this and it looks like we're going to be inside the thing, and we just zoom and zoom and zoom, eventually we fall out. And if I take another place like this and think we're going to hit the middle of it, well, we fall out. And the only place where there's actually any substance is right there at the center points, and all it is an infinite number of copies of itself. Quite mind-expanding.
Can we ask a question now?
Please, yeah, no, I want to encourage interaction, absolutely.
With Lovelock's Gaia theory, part of the element of what he discovered about Gaia was the ability of self-regulation. And so self-similar as above, so below, what we find in nature, as you're finding here in this self-similar quality, how does the self-similar quality relate to Gaian self-regulation?
The best way I can answer that is just to proceed with my talk, and if I haven't answered your question fully by the end, then we can revisit it. But I will show different examples of fractal systems in nature that hopefully will satisfy that.
Another question, does that little figure have a name?
This is the Mandelbrot set.
That's it?
Yep. It could be called many things. Many people think that it looks like a Buddha. It may be coincidental that it looks like a Buddha, or maybe the Buddhists are onto something. Many people who see my shows find it a very deeply spiritual experience because we're journeying into the infinite. And it is something that's infinitely perfect. It's way beyond the ability of any mortal artist to create something of this level of perfection. And then there's the symmetries. This is the eightfold path of Buddha, all kinds of things like that. But let's actually take one little journey into one of these replicas. Just to let me zoom back out to show where we are. And explore the edge of one of the little copies, because then we find another level of structures, another order entirely. So if we go into the Seahorse Valley of a little copy, it's the same as the big one, except it's now embedded in a bunch of these little tendrils. And in fact, there are always a power of 2 number of these tendrils because it's always bifurcating. If you step back, you'll see that there are originally two arms from the top and the bottom joining in this thing, and then there's 4 when you add these branches there, and then it bifurcates to 8 at this level, and then there's 16 at the next level. If I cycle the colors, we can see it a little better. And then there's 16 at this level, 32, 64, et cetera. So when you get down to this level and you look at it, now there might be 1,024 of these arms and 2,048 of this scale and 4,096 at that scale or something. But if we go and look at one of these tendrils, now we'll see a new pattern emerge. And we haven't observed this structure yet. And this is something I like to call a virtual Julia set. And that's because it looks very much like what we call a Julia set, except it's not. And I may or may not have time to get into the distinctions of this. But let's pay attention to what happens in the middle of this, because if you look at the symmetry here on this very interesting object, it's what we know as twofold rotated symmetry. Basically, there's 2 copies of the thing, one over here and one over there. And if we go in the middle, the middle points are always the places to find interesting things. So now we've had a doubling of the symmetry, and now we have 4-fold rotated symmetry. And in the center of that, it bifurcates again, and we have 8-fold rotated symmetry. Then 16, 32, et cetera. Again, this period doubling cascade is a very, very common phenomenon in chaos theory and fractals. And in the center, of course, then we have our 3rd order copy of the Mandelbrot set. So now this is a nested version embedded within another one. Now, you might have remembered that the different areas that we go to impart different styles to the stuff that we're exploring. And so if you're exploring in the Seahorse Valley of one Mandelbrot set, but then you find a little baby copy, an embedded replica, and then you go explore somewhere else in that one, what you can do is you can nest the styles, like I've done here. So we have this long spiky stuff on the outsides, and then this Seahorse Valley-like material on the inside. We can keep doing that indefinitely. What this allows us to do is, once you understand the rules and the principles that govern the organization of this object, and these organizational principles are universal. So once you understand them, you can actually very deliberately sculpt the material that you want to form. In other words, this thing is infinite. And if you know how to find it, you can find anything in here. It's a very, very intriguing idea. You can basically add shapes together and build on symmetries. And the deeper you go, the more interesting, complex, and beautiful the thing tends to become. It's very much unlike a regular microscope, which we're accustomed to, which is when you zoom into it, eventually you run out of resolution and it just becomes blurry. This thing gets sharper the deeper you go. Now, it takes a lot of patience the deeper you go, too. I like to call this tool, by the way, this program, a hyperscope, because it's both a telescope and a microscope. It allows us to travel over great ranges of scale. Now, the great thing about this is that I'm about to give this program to you all for free. Okay? It's a gift. I can't take total credit for it. It's an open source project that was originated in the Czech Republic by a computer science programmer named Jan Hubička, but I've contributed to the project, and I've customized it and given it away now to thousands of people who have downloaded it from our website, fractalfoundation.org. And I would encourage you all to do so as well if you're at all interested in exploring this object yourselves. It is incredibly addictive, but it's a good kind of addiction. And there's so much to learn here. I'm going to actually come back to this program in a little while. We could spend 2 hours just zooming in this thing, but I really want to put this all in the context of fractals in nature as well. So let me just leave this program for now with a couple of pointers that well, first of all, I'm running it on a Mac, but it exists for the PC as well, although the Mac version is a little bit nicer because I've helped customize that one. But it comes with very, very useful tutorials. So if you want to learn anything, this is a great place to start about how these fractals work, the features of the program, of which there are many, many powerful ones, and something about the math of fractals and stuff like that.
Oh, thank you.
So by all means, explore to your heart's content, and you'll never be bored again. I haven't been bored in 25 years. So let's see. Well, before I leave, I just want to point out that there are a whole bunch of other formulas built into this, and you can just access them by hitting the number keys. This is just a very brief tutorial, and the capital letters. And we find a whole bunch of other fractal formulas here to play with to your heart's content. And you can all explore them in the same interactive fashion that is just mind-boggling, but different formulas create different patterns, and yet they're all really, really interesting and beautiful. All right, so let me jump out of here for the time being. I will come back, if time permits, and show you some more amazing things about fractals in an interactive fashion like that. But let me jump back into my official slideshow and just tell you an overview of some of the things I might be able to get to. This is a nice outline, but fractals being a subset of nonlinear science, don't expect me to cover these in a linear fashion. I'll touch on what I do as it comes. Yes, I put this here to remind myself of some of the fun things to talk about. I want to make sure to talk about fractal applications, because fractals are not just the language of nature and science, they're also becoming increasingly important in engineering. And so people are starting to build things based on fractal ideas. So I'll show you some examples of that. And, well, let's just jump in. OK, here's a really simple illustration of a fractal that explains the basic concept. It shows you, first, you don't need a computer to generate fractals. This is a fractal that I teach kids in elementary school how to make. And so all you do is you draw a triangle, and then you connect the middle points of the big lines, and you connect them. And you draw a new triangle in the middle, and you color it black. And then what you're left with are 3 triangles, here, there, and there. And you do the same process to each of those. So you draw the middle triangle black here, over there. Now you're left with 9 triangles of this scale. And you do the same thing, draw the middle triangles black, and now you're left with 27 triangles of this size. And then you can do the same thing, and you're left with 81 triangles at the next scale, and so on. And there's no practical reason why you have to stop until your pencil is no longer sharp enough to make really tiny little triangles. This illustrates the power of these concepts, okay, that a fractal is a very complex pattern, but all fractals are formed just by repeating a simple process over and over and over again. Okay, so we do that in a geometrical format by taking the same rule of chopping out triangles. We do that in the mathematical fractals I showed you, like the Mandelbrot set, by simulating a process with an algebraic equation. And we plug in a number and we get an answer. And then what we do is we take that answer and we plug it back in to the equation as the starting value, and we get a new answer. And then we plug it back in through a mathematical feedback loop, which I'll show you in a little more detail. But what we're doing is just repeating a simple process over and over again. The other thing about fractals that this illustrates, of course, is self-similarity. So that a little tiny piece looks like this piece, looks like this piece, looks like this, looks like the entire object. In a sense, it's sort of holographic, because any piece looks like the whole thing or carries information about the whole object. But let's look at some examples of fractals in nature. So this is actually a simulated fern, but it illustrates this idea of how the plant kingdom is full of fractals. And you can see that a little piece of the fern kind of looks like the whole thing, and a little piece of the piece looks like the whole thing again, and so on. Now, mathematical fractals go on forever, but mathematical or natural fractals don't. They exhibit self-similarity only over a certain range of scales. It's important to remember that, but nonetheless, these things still have wonderful fractal qualities. Here's one of my favorite kinds of fractals. This is an edible fractal. It's, they call it broccoli romanesco. You can buy this at La Montanita Co-op. I like to call it froccoli because it's so fractalicious. And I sometimes take this to the presentations that I give and give it out as hors d'oeuvres. And you can break it apart into little clusters, which when you zoom into it, they all look more or less like the whole thing. And you can keep zooming into it, and it's just extraordinary. It's absolutely an amazing vegetable. I don't know if they have it at this co-op. I assume they probably do. It's really delicious, too. It's better than either broccoli or cauliflower. Kind of tastes like artichoke hearts a little bit when you steam it. But the wonderful thing about it is that you can really perceive and appreciate the fractal texture on your tongue as you're chewing it. You feel all these different scale bumps. No, it's fun. Try it. The other thing that's wonderful about this is that it has this spiraling form to it, right? Where we find this very commonly in nature, in sunflowers and pine cones and things like that. And it's a very common fractal form. It relates closely to the Fibonacci sequence, which is an arithmetic fractal that I don't really have time to get into, but it's a lot of fun. So we find the same kind of spiraling pattern in a lot of different systems. And spirals are one of my favorite classes of fractals. I'm wearing one. I often wear fractals whenever possible. And, well, I'll illustrate how you build a spiral and why a spiral is a fractal in a little while, but when we look at some other ones. But let's jump outside and look at some trees. In the wintertime, especially when the trees are missing their leaves, you can really appreciate the fractal structure here. So the other main class of fractals that I like to teach people about are the branching family of fractals. So basically, there's the spiraling family and the branching family. And trees are a great illustration of how fractals work. And there are lots of different styles of trees, different species of trees, but they all basically proceed through this fractal process of growth. Okay, so a seed is planted, a shoot comes out of the ground, and it branches. And that's the essential thing that happens in building a tree. And then it happens again. Each of those branches branches again. And then each of those branches branches again, and each of those branches branches again. And in a big tree, it might branch 8 or 9 times. Okay? But you know what happens when you double a number, and then you double that number, and you double that? You very quickly end up with very big numbers. And that's what's going on here. we end up with a lot of little tiny twigs on this thing. And this explains the self-similarity. So a little piece of the tree over here looks like a little piece of the tree over there, looks like a little piece over here, which kind of looks like the entire tree. Now, it's not perfectly self-similar, like the mathematical fractals. And there's a number of reasons for that, different physical laws about scaling, and also there's environmental factors, such that if a deer is chewing on a leaf here when the tree is just a seedling, then it introduces an asymmetry, and then 100 years later, that will be reflected in the overall structure of the tree. Okay? Plus, there's all the chaos of the wind and the weather that are unpredictable.
What about family trees?
Family trees. I will show you some family trees. It's an excellent, excellent question. But let's look first at some other examples of branching fractals. You can see the branching pattern in the structure of a leaf. You can find it inside your bodies too. The animal kingdom is full of fractals as well as the plant kingdom. This might be more recognizable if I flip it over such that it looks like the lungs, but I like to do it upside down so it looks more like a tree. But our lungs are wonderful examples of fractal structures. Okay, so the lungs have this amazing property. Well, first of all, I always like to ask my audiences, why do you suppose the lungs and the trees have the same geometry? What's underneath that? Breathing, surface area, excellent, perfect. So it's because they do the same function. They have the same role. So they're both organs that are specialized for respiration. And what that involves is exchanging gases with the atmosphere. Animals breathe in oxygen, breathe out carbon dioxide. Plants do exactly the reverse. They breathe in carbon dioxide, breathe out oxygen. But they both need to exchange gases with the atmosphere. And to do so, they need a large surface area, as large a surface area as possible. Now, our lungs have a very small volume. Okay, they're very compact. They fit inside our chest very nicely. They're only about 2 liters in volume. But they have a very large surface area. Does anybody know roughly what the surface area of our lungs is? Anybody want to guess? An acre? It's not quite an acre. It's about 100 square meters, a hectare. So 100 square meters is like a tennis court. It's bigger than this entire room. If you could flatten out your lungs and spread out all this fractal branching pattern, it would fill up a huge, huge surface area. Quite an amazing feature. Now, in the kind of geometry that we learn in school, there are very simple, straightforward relationships between surface area and volume. Like with a cube or a sphere, we know how that works. Here, it's much more interesting and much more unpredictable and much more useful sometimes. So I show this because we can think of the trees as being the lungs of the planet, and who knows what the surface area of a forest is. It's incalculable. Right, here's another interesting fractal picture, and one of the fun things about sharing fractals with people is that because they exist at all different scales and in all different systems, we don't know necessarily what we're looking at until I tell you. So this could be a microscopic cross-section of some internal organ or something much bigger. Or it could be an erosion pattern. It's a watershed. It's a network of rivers as seen from space.
How do you know that's actually a fractal or not just something that looks like a fractal?
Well, there are people who are really concerned about that question, the rigorous mathematical sticklers who say that's not really a fractal, it's only approximately a fractal. To me, I don't really care. It's close enough. It's not rigorously self-similar, but if you look at a little piece of it, it looks kind of like the whole thing. It's got this branching pattern that repeats and repeats and repeats. And I think we know just by experience that we can find little tiny streams merging together. If you look at arroyos, they look like big canyons, right? They have the same geometry, and they don't go forever. I mean, I'm not going to pretend that these things are infinite, but the other thing that lets me say with some confidence that, well, I call this a fractal is because it's formed by repeating a simple process over and over again, ending up with a complex, irregular pattern that occurs at many different scales. And so the repetitive process that forms this is just that rain falls and flows downhill. And then the next time rain falls, it's going to follow the same pathway because it carves it out a little bit, makes a little tiny channel. And so then there's feedback. And the next time it happens, it gets even deeper, and then even deeper. And then over millions and millions of years, we end up with things like the Grand Canyon. Now, this fractal is fun because this doesn't exist in an animal or a plant. It exists on the surface of the Earth, which is not alive in the classical sense, but it is alive in the Gaia sense. It is alive in terms of being a complex system or a dynamic system that is always changing and evolving, eroding, growing, moving. And so things happen repetitively that cause fractals to form. Now, this fractal takes a long time to form, but this fractal happens not in a million years, but in a millionth of a second. So what I like showing about this is that we can find the same kinds of pattern at all different scales, both in space and in time. We find tiny little microscopic fractals, we find gigantic fractals, we find very slow fractals and very, very fast fractals. This one, it's an amazing picture. It's very difficult to capture lightning pictures. And this one I actually have, I didn't take that, but this picture, hang on, I just got in the mail today. If I can find it. Yes. An object, it's a real fractal, built in a piece of plexiglass. Okay, so this is a 3-inch diameter plexiglass disc that has had 10 million electron volts of energy beamed into it, and then rapidly discharged like a lightning bolt in a piece of plastic. And you can come up afterwards when it's kind of hard to see in the dark here. So when we turn the lights on afterwards, I invite you to come look at it up close. But it is just exquisitely beautiful. You can get these online at teslamania.com, which is where I bought this thing. And they have a nice collection of these things. Some of them are really big. They get pretty expensive when they're big. But it's an amazing little fractal version of a lightning bolt captured for posterity. And it's just really amazing. OK, let's shrink down in scale even further and look at some branching fractals inside our heads. So I said my background in science is as a neuroscientist. And these are cortical neurons from the visual cortex. And boy, I don't have enough time to tell you how this thing works. But no, I sure don't. But I'll give you the 30-second version of how the brain works. And that is that we have about 100 billion neurons in our brains. 100 billion. But more important than that is the number of connections they make among themselves. Okay, so one neuron doesn't just communicate with its nearest neighbors. One neuron can communicate with thousands or even hundreds of thousands of other cells all throughout the brain. And it's that interconnected network that gives us the amazing abilities we have. So every time you learn something, what's happening is you're changing the strengths of these connections called synapses. You're either forming new ones, or you're eliminating old ones, or you're just changing the strength of existing ones. And it wouldn't work if neurons were not fractal, because then they could only communicate with like a dozen cells in their immediate neighborhood. But now because of this fractal branching pattern, they have axons and dendrites. Dendrite comes from the Greek word for tree, because these look like little tiny trees in your head. And that is what allows our brains to form these complex networks. Here's an interesting network of sorts of a different scale entirely. I like this because it looks a lot like a micrograph of the brain, but this is not a neural network. This is a cosmological simulation of the distribution of galaxies in the universe. So the scale bar here, in case you're not familiar with megaparsecs, is roughly 15 million light years. Okay? So these bright dots you see are not stars, they're entire galaxies. And the galaxies are not smoothly distributed homogeneously throughout the universe, as a boring god would have created, but they're distributed in these filament-like networks that somehow look strikingly similar to our brain. If that means anything, I don't know, but it's certainly interesting to observe.
Well, isn't it self-similarity?
Yes, it is. But does it mean anything beyond that? I don't know. Let's jump back down into our bodies, and I'll show a couple more examples of branching fractal patterns. What we're seeing here is the circulatory system in your eyeball. So this is the retina in the back of your eye. But all throughout your body, this applies. Every single cell in your whole body, and we have quadrillions of them, they all need to receive blood. They need oxygen and nutrients, and they get that through the circulatory system. And you can think of this like the plumbing system of the body, except unlike the plumbing system in a building, which only goes to the bathroom and the kitchen and maybe the laundry in your house, the blood vessels take blood everywhere. They thoroughly penetrate your entire bodily tissue. And the only way that can happen is through this fractal branching pattern. So it's a very, very useful structure. And just like we had a very large surface area in the lungs, there's a nice statistic about the number of blood vessels we have, or the length. If we were to put them all in a straight line and connect them, measure the length of blood vessels we have in our body, does anybody know or want to take a guess about how big that would be? It's not quite to the moon. It's several times around the Earth. It's about 100,000 miles of blood vessels in your body. Most of those, of course, are microscopically small capillaries, but still quite impressive. All right, now I made a note to myself to make sure to talk about some engineering applications, just because I really like seeing fractals come out into applications. This is not just all theoretical stuff. And one of my favorite things is this practice of what we call biomimicry. And this is where humans derive inspiration from nature. Nature, after all, has been evolving these patterns for several billion years. And there's a very powerful feedback loop at work in evolution. When something works, it succeeds and propagates. And when it doesn't, it dies away. So these patterns in nature have been refined. And it would behoove us to look to these patterns for inspiration when designing things. So here's a cooling circuit for a computer chip that is very strongly inspired by the circulatory system. So what you do is you drop in liquid nitrogen into that central reservoir, and it distributes it uniformly in this very nice network. Okay, it's the faster that these computers get, and I'm always rooting for them to get faster, the hotter they become. And so it's more and more important to cool them effectively. So that's where fractals come in like this. All right, I'm just going to take a brief segue into some more applications. This is the prototypical hydrogen car that's always 20 years out in the future. What's interesting about hydrogen cars is that the technology already exists and has existed for a long time to turn hydrogen into electricity. What's missing from this equation is the ability to store hydrogen effectively. Okay, so we need to be able to carry enough hydrogen so that you can drive a couple hundred miles at least. Right now, the state of the art in hydrogen storage will let you drive about 50 miles. Okay, otherwise you end up carrying thousands of pounds of hydrogen tank. So there's a lot of very active research in this. And it turns out that it's not very effective to compress hydrogen. What's much more effective is to adsorb it onto the surface of a material, like certain metals, like nickel metal hydride is an example. And it turns out that the more surface area you have of your substrate, the more hydrogen will stick to it. And so it has become very, very useful economically to create these structures with very, very large surface areas. And that's where fractals come in. And these people are engineering materials now that, if you look at the graph here, this is an amazing axis here. What this says is we have materials, and this is actually even a little bit out of date. There are now materials that can hold, or that have 4,000 or 5,000 square meters of surface area per gram. So you can make a powder of some complicated material that has more surface area. I mean, it's hard to imagine all of that surface area compressed into a teaspoon of powder. Very impressive. Even more impressive than our lungs, which only have 100 square meters in this very large volume. So pretty amazing application of fractals. Maybe they'll get to the point where we can actually drive hydrogen cars, but I'm not betting on it. All right. The stock market is another great example of fractals. The applications of fractal theory. Of course, what we learned from chaos theory and fractal analysis of these things is, well, you can see a stock price is a fractal. If you look at it at different time scales, over a year or a month or a week or a day, or if you're day trading and look at it jiggling up and down by the minute or the second, it all has the same chaotic, rough, jagged, fractal-like behavior. Now, there's a lot of interest among chaos theoreticians and people trying to make a lot of money out of predicting the stock market, but if you really could do that, then people like me would be really rich, and unfortunately, it's not really possible, as far as I can tell, to actually predict the stock market. What we can tell is how unpredictable it is. So, and we can quantify that quite well. One last application of fractals are in cell phone antennas. And I really want to get a cell phone demo that I can open up and show to students. But they actually do have these little Sierpinski triangle-like antennas made out of gold foil inside them, some of them. And it turns out it's very useful to engineer a material like this because it's a multi-band antenna. It has structure at different scales, so it can pick up lots of frequencies and be very compact, so you don't need an external antenna out of your cell phone. I'm always trying to find ways to engage kids' interest, and if I can show them fractals inside their cell phone, I think that's pretty cool. All right. Let's jump back into spirals, because I love spirals. So yes, this is Hurricane Katrina from a couple of years ago. And while it was a very dangerous, destructive, awful storm up close, seen from a distance, it's a very beautiful pattern. And nature spontaneously forms these spirals. This comes out of the motion of fluids, and turbulence is full of spirals. You don't have to do anything to the atmosphere to form spirals, and it's absolutely gigantic. It's roughly the same size as our entire state of New Mexico. You can see Florida there off to the right. But it's not even close to as big as some spirals get. They get very, very much larger. This could be 100,000 light years from side to side, and a typical galaxy might have 100 billion stars in it. 100 billion stars, that's about as many neurons as we have in our brain, just for point of comparison. And they spontaneously self-organize in these beautiful spiral patterns. I could give a whole talk on spiral dynamics in galaxies, but I won't. I'm just going to tell you something really cool, which is that there's actually a uniform distribution of stars in the galaxy here. The spiral is what showing, it's a compression wave of newly formed stars. And the newly formed stars tend to be very bright, and then they burn out quickly, only in a few million years. The normal stars, the majority of stars are dimmer, and they last for billions of years. But there's a short-lived band of very bright stars where the stars are being formed. So this spiral wave is constantly forming and spiraling through the stars. So the stars might actually be spinning in one direction, and the spiral pattern could be spinning through that galactic mass in a different direction or different speed. Quite an amazing thing to appreciate. All right, now I'm just going to take this little guy to explain why I like to say a spiral is a fractal. Because you can see it at all different scales, and because it's formed by repeating a simple process. And this is a great illustration of that. The organism that creates this doesn't know what it's doing, right? It doesn't have a blueprint of the shell in its mind. It doesn't even have a mind. It has just a few little neurons stuck together. What it does, though, is it keeps building little sections on its shell. It keeps adding a new one, and then a new one, and then another one. And it keeps doing that, and each one is a little bit bigger than the one before and a little bit rotated. And it's that combination of expansion and rotation, twisting and growing, that forms a spiral. And those are two very common, simple forms of motion, expansion, rotation, and all you have to do is combine them, and out swirls a spiral. You can find them very small scales in the tracks of subatomic particles in a magnetic field, protons and electrons zipping in opposite directions and things like that. And in the turbulent motion of fluids, again, not at the scale of the atmosphere, but in the side of a soap bubble. And, oh boy, let's see, how am I doing on time? Actually, we're all right. This is here to remind me about the butterfly effect. Okay, so that together with the hurricane, it's one of the principles of chaos theory that I really find important and valuable to teach. The butterfly effect, for those of you who don't know what I'm talking about, refers to this idea that a small change to a system can lead to big differences in the outcome. We call that, mathematically, we call it sensitivity to initial conditions. So you change the initial conditions a little bit, and you get a very different thing coming out of it. This is the basis of a nonlinear system. It's all around us in the world, but somehow we like to ignore it. And our culture teaches us to think linearly. That's how we're brought up, expecting that if you do something, you'll get a certain answer. If you do that thing twice as hard, you'll get twice as much of an answer, which is a linear response. But really, that's not the case. Now, just to step back and explain what the butterfly is, it's the idea that a butterfly, when it flaps its wings, it impacts the atmosphere. And that impact doesn't just fade away and dissipate. It actually ripples out and affects air molecules all around that affect other ones, that affect other things. And that one flapping of the butterfly at a specific point in space and time could end up participating in the causing of a hurricane on the other side of the planet 100 years from now. Now, there's no way to causally link these two things. You can't blame a specific butterfly. Please don't. But nonetheless, there's billions of things that conspire together to form hurricanes. But never underestimate the power of butterflies. Now, there's a flip side, a corollary, if you will, of the butterfly effect, which is very important to teach as well, and that is the law of unintended consequences, which is that small things that you don't pay attention to might actually end up growing out of control and becoming a real problem. So that, for example, we were talking on the radio this morning about invasive species. And so humans are always way too clever for our own good, thinking, there's a little problem. I'm going to fix that problem by introducing some animal or some plant that doesn't really belong here, but it's going to eat these things that I don't want. And then it does, and then it eats everything else too and gets carried away out of control, and now there's rabbits all over, or cane toads all over, or kudzu all over, or all kinds of things that don't really belong in the ecosystem the way that it evolved to be most stable. And the thing about nonlinear systems, yeah, well, there's a lot of things like this. But the thing about nonlinear systems, and especially with positive feedback, is that it's very hard to undo something like this. You can't put the genie back in the bottle. You can't put the toothpaste back in the tube. It doesn't work in both directions. You can't just reverse it and say, oh, I wish I hadn't done that. Let me hit undo. The universe is not so forgiving. All right, this, well, I'm trying to decide how much detail to go into about this. This is a historical trace of the discovery of chaos theory. Okay, so chaos theory was discovered in trying to predict the weather. So Ed Lorenz was simulating what happens in the atmosphere and trying to predict the weather. And he fed certain things into his model and predicted the next day's weather. And then what he did is he took the answer for what tomorrow looks like and he fed it back into his model to get the day after tomorrow's weather. And then did that again, and then the day after that. And what he found was an amazing thing, which is that he tried to reproduce his data. And he didn't get the same answer, even though he put in the same numbers. And that's totally screwy, right? That can't work. That's not OK. If you're modeling something and you plug in numbers, you want to be able to reproduce it. Science is all about reproducibility. But chaos theory throws a wrench into that. And it turns out that there was a small rounding error in the 9th digit of precision in his computer. And so there was a little fluctuation, and sometimes it would be one digit, and sometimes it would be another. And he went back and looked at it in detail and discovered that that error was amplifying. It was growing because it gets fed back into the system the next day, and then the next day, and that error keeps growing. And so what we're seeing here are two traces. I think this is temperature over time. But there's actually two traces overlaid here. And here's day 1, here's day 2, here's day 3, they start to come apart. Here's day 4, and they're almost anti-correlated by here. They're completely disconnected. And what that tells you is that you can have no confidence in this prediction. So a lesson here is that it doesn't matter how powerful our computers are. It doesn't matter how sophisticated our models of the atmosphere are. We will never be able to predict the weather more than just a few days out. Okay? We'll never be able to. And that's because of all the butterflies out there, basically. Think if a butterfly can have that power, what does a truck driving down the highway do to the atmosphere, right? Or an airplane. And well, I'm just going to leave it at that. There's a lot more to talk about with chaos theory. But let's jump back into the fractals because that's the fun and beautiful part. All right. So one of the things that we talk about in fractals and chaos is this idea of a strange attractor. And this is pretty much a very difficult abstract concept for a lot of people to get. You have to deal with complex phase space and all this stuff. But here's how I teach a strange attractor. Okay? So as a balloon pilot, I love exploring the atmosphere. And the atmosphere is a wonderful example of a nonlinear system. If the atmosphere were linear, we would have 800 balloons taking off from Balloon Fiesta, and we would all fly in a big clump, and we would all land right next to each other. Right? Now, we were taught to think this way. The weather forecasters will tell us with a straight face the winds are going to be out of the west at 10 knots and blah, 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 like that's really true. Of course it's not. What happens is the wind is going 800 different directions. We go 800 different destinations. We're swirling and twirling and doing all this complex motion. And what this illustrates are the possible outcomes of very close, similar starting conditions. Not identical starting conditions. We're all taking off from the same field in the same few minutes, but we're not identical. Right? So two balloons take off, and the atmosphere will spread them apart. It's very hard to fly next to another balloon for long distance. It's a good challenge. We try to do that sometimes to fly together with our friends, but it's almost impossible. Fire is one of my favorite examples of fractals in nature. You don't typically think of fire as a fractal, but it's a turbulent phenomenon. and it occurs at all different scales, and it's feedback driven. So the way that fire actually works is that when you heat up a piece of wood, it doesn't burn. The wood is not what's burning. When you heat up the wood, it releases gases, mostly methane, and the methane is what catches fire and burns and releases heat. And then that heat causes the wood to release more gases, which ignite, releasing more heat, which releases more gas. It's a positive feedback loop. Positive feedback loops are incredibly powerful and very dangerous. They're very hard to control, right? So you can, the power of it is illustrated by the fact that you can light an entire forest on fire with a single match, right? And the fire will grow and grow and grow, and it's very easy to grow to the point where you can't put it out. Now, you can't, of course, just take a match and light a log on fire. You need all those intermediate pieces of wood, which is where it's very convenient that trees are fractals. So they have all these different sizes, scales of kindling in between. But I like illustrating that as just a quick illustration. Boy, it's the coastline of Britain, but I want to take this opportunity and see if this is going to work here, see if we can actually do it in a more dynamic way. Even though I'm not online here, I tried to, whoa, that didn't do it. Hang on. What I want to do is show you some fractals on the Earth. And I'm just trying to go full screen. All right. So in keeping with our theme of zooming to infinity, let's zoom into Earth, and I'll show you some fractals right here at home. If any of you have not played with Google Earth yet, I highly recommend it. It is a wonderful, wonderful exploring tool, a toy, an amazing lesson. And there's all kinds of fractals. Right here in New Mexico, look at these river networks that we have. And there's actually more detail here, but I'm not streaming. I'm relying on what's stored in memory. This is Artesia, I believe. I'm actually going there next month to teach at Artesia High School. Yes, there we are. And here's some more fractals over here. I'm going to incorporate high-res animations of this in my full dome show at the planetarium just as soon as Google gives me the rights to, which should be soon. But there's any number of really, really beautiful fractal patterns in the surface of the Earth. Let me step back out into space, flip around over here. Hold on. Let's go to Europe. Wait. Whoa, no, I didn't mean to do that. And rotate it to face upward. And now the foundation question of chaos theory, or I mean of fractals rather, was how long is the coastline of Britain? Okay, so I want to illustrate the problem that's posed by this question. It depends on how closely you measure it, and that's a kind of a frustrating answer. Okay, well, so let's zoom in and look, and we'll see more detail. The closer we get, the more we find. And if we measure with a measuring stick that is smaller, we'll end up with a larger value. Okay? And what I discovered in doing a little research on this is that the USGS, when they survey coastlines, they measure with a 55-kilometer long ruler. That's a very long ruler. You miss a lot of details. But they want to know how long the coastline is, so they found a way to answer that question. That's more satisfying than infinite, because that's the real answer. But it's not very useful. All right, so if you look and if you zoom in, you can just keep on zooming. And you see more and more and more detail right down to the beach. This is an amazing program. It's also free. It's a fractal zoomer on the Earth, and you can see there's fractals right down to the point where there's rocks. And rocks are great examples of fractals in nature, because a rock looks just like a pebble, looks like a boulder, like a pebble, like a grain of sand, right? If they're all of the same mineral, they all have the same jaggedness and roughness. And if you really wanted to measure the coastline, you'd have to go around every grain of sand, which of course is bumpy and jagged like that. So I'm not going to zoom any more fractals in the interests of time, but let you download Google Earth yourself. It is just extraordinary. Actually, you know what? I'm going to take you on one more fractal on the Earth because I can't help myself. All right, let's go to Bangladesh. Because here's a different kind of fractal. Instead of the river network where the rivers are merging, if we look at a river delta, you can see where rivers are splitting, and they form these. Let me see if I can just zoom into it. Yeah. All right. So if we, oh, come on. I'm not going to be able to do this because I forgot to download this data before I came here. It's not stored in my computer. Really sorry. Go look, explore the Bangladeshi Delta yourself. This is the Ganges River and a holy place for many, many people in the whole world. And Google Earth, earth.google.com. It's free, and you can spend a long time flying around the world. It is so fun to do. Fractal zoom? Yeah, did you say? Well, I'm zooming, that's all. I'm just looking at different resolutions. That's all I'm talking about. But let's see. Trying to manage my time. Fractals are infinite. I could talk about fractals all day, all week, all month. I'm actually involved in a very exciting program with the State Public Education Department to develop an online fractal math course, which is really exciting because most of the time I go into classes and I teach fractals for an hour or at most a half day. And now I'm getting the opportunity to go into significantly more detail and have exercises and applications and things you can play with to explore the beauty of nature and nonlinear mathematics and how they connect. So really excited about that. Trying to scan through here. Ah, yes, I promised someone family trees. Let's show some family trees. Here we have the relationships in the dogs. Dogs, wolves, foxes, and so on. And so we can see the x-axis is time, millions of years before the present. And you can see that our evolutionary family tree branches. And it branches, and it branches again, and again, and again. And this is the process of feedback at work in evolution, that what works survives and becomes a new species and eventually separates off from what it came from. Here's a family tree at a more familiar level where you can see human relationships. But of course, this works all throughout nature. The baboons in Africa have cousins too, right? And grandparents and nephews and uncles and all these same kind of relationships. And at some point, we are all connected. And this is a very simplified version of the unified family tree. This is a picture showing 3,000 species of life out of approximately 9 million that we've cataloged. Okay, so you can't see all the fine degrees of branching there. This is freely available. You can download it. They recommend printing it 54 inches wide in order to see all the little species at the edge of this thing. So it's an amazing piece of work that humans have done. And my favorite part is this guy up there. You are here. And that's, of course, what's of interest to us. But I would search for taxonomy tree of life, and you'll find it. That's how I found it. So
it just makes me think, however, that if you look at the pictures of everyone's face all taken together, that's a fractal structure as well. Isn't it?
if you averaged our faces together?
No.
What do you mean?
If you look at everybody's center. I mean, if you kind of make your vision spread out and look at everybody at once when you have a fractal picture.
Yes.
Everybody at once.
Well, we're all, in a sense, we're all unique, but we are all parts of this bigger whole, and we're all connected genetically, is what this illustrates to me. But I don't really know how to go into it in much more detail. I like to show this because this is what I do. I travel all over the state of New Mexico teaching kids as young as, these guys are third graders, but even down into kindergarten, because what we have with fractals is a real opportunity to get people excited about math and science. And I love reaching kids before it's too late, before they've discovered that they don't like math yet, right? And that's usually by about 7th grade, in my experience. The younger they are, the more excited they are, the more receptive they are. And kids love fractals. They just eat this stuff up. All kids are born scientists and they're born artists. And so one of the things we're doing, it's really exciting, we have a grant from the PNM Foundation to take this portable dome to places around New Mexico and do the same kind of show in schools. So very, very, very exciting. That's why I'm going to Artesia soon. Couple of other things, just wanted to show the program. Now we get to the fun part, okay? I promised I would explain the algebra. All right, for those of you who've been waiting for the math, here's the math. All right. Math is the language of nature, and when you present it as such, people care about it. If they don't understand the context or why you would want to know this, then it's just boring. Kids actually really care about fractals, and so then they want to learn how the algebra works that generates these patterns. And this one illustrates it a little bit better. But look at the arrows in this equation back here. What we're doing is we're plugging in numbers to this equation. Z new equals Z old squared plus C. And these, by the way, are complex numbers, which means they occur in two-dimensional space. Every point in the plane is a value of Z or a value of C, okay? And what we're doing is just plugging numbers in. We're testing different values of C to find out what happens. We're exploring the fate of different starting conditions. This is where chaos theory comes in and the butterfly effect and all of that. So 2 points might have very different fates, even though they're right next to each other. And that's what's so interesting about exploring fractals. What happens is inside the Mandelbrot set, all the points have a common fate. Outside the Mandelbrot set, all the points have a common fate. Now, generally, what happens when you square a number? It gets bigger, exactly. So if you take that answer and plug it back in and square that again, it's going to get even bigger. And then you do that over and over again, you keep squaring the answer, it eventually goes to infinity, and it probably doesn't even take that long. That's what happens to most points. All the points in blue outside the set go to infinity. All the points in the black area stay finite, because some numbers get smaller when you square them. Can anybody think of an example? No, negative numbers get bigger when you square them. They turn positive. A number between 1 and 0, a fraction, exactly. Like a half. When you square a half, you'd get a quarter. You plug that back in, you get exactly a 16th. So you can do this, and we're exploring the fate of different points. Now, what's interesting is the edge. Okay, so I'm now going to jump back out, and go back into the chaos program. Oh, shoot. Sometimes it crashes when I do this. All right, so you get what you pay for. One moment. what I want to point out is that the outside of this thing is completely boring. All the points go to infinity. The inside is completely boring. It's all black. Right? If we take any point, even one of these bulbs, there's no more detail there to explore. What's very, 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 very interesting is this stuff right at the edge. And this is where the infinite complexity of fractals is so interesting. Because a point here, when you plug it into this equation, goes to infinity. But a point over here, very close by, arbitrarily close by, you can choose 2 points that are infinitesimally close to each other, but not identical, can have totally different fates. 1 point will go to infinity, 1 point will stay finite. Couldn't be more black and white than that. And yet, you can never find that edge because you can always keep zooming and find smaller and smaller points that are closer together, and yet they could still diverge. Yes, question?
What do you mean by they stay finite? I'm not
Okay.
quite sure what, I know it.
No, yeah, for sure. Let me illustrate that. I glossed over that. There's a picture here. This one, if we look at the orbit diagram, this is called. So a point here that starts outside the set, you plug in this number, you get that answer. You take that answer, you plug it in, you get this answer. Then it goes here, 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 and it follows this orbit through space, zipping outward, getting bigger, spiraling outward. And depending on where you are in this thing, they'll have different geometries, what we call different periodicities. It might have a period 3 kind of behavior, or a period 5 behavior, period 4 behavior. Like this is a square, a period 4 thing. But outside the set, it spirals outward. Inside the set, you get a point like this. It goes here, and then it goes here, and it spirals inward. It converges to a fixed value. Or that's what happens to the points in here. In this bulb, it converges to a stable periodic oscillation between 2 points. It bounces back and forth, but it's captured in a stable orbit. Here it's...
As you feed back in your new,
Uh-huh.
so they kind of, you keep getting the same answer over and over.
Exactly.
Oh, okay.
That's what I mean. Now it can...
Outside the set, you never get the same answer.
Nope.
It just gets bigger.
It just
Give
gets
me an
bigger.
example of a starting number?
1 plus 0.5i. They're complex numbers, okay? That's actually a really good question. Just to put this in a coordinate system, I should draw the axes on here sometime. This is the origin right here, 0, 0. This point in the center of the circle is -1. This is -0.75. And this is 4. I think. Yeah, okay. But in any case, it's bounded, and it's relatively small. So most points get really big when you plug them into a squaring operator. Now, what's fun about fractal math is that it invites you to play with algebra. Okay, so here we can now change the equation, and we can graphically see what happens. We can explore the behavior visually. So here's the equation z cubed.
Z is the imaginary part?
No, z is...
C is the imaginary.
No, they're both complex numbers. Z starts with 0. And we were exploring the fate of different values of C. If we were looking at Z, we can do that, and we get what's called the Julia set, which maybe I can show you a little of. But here we find the Mandelbrot set for the z to the 4th power equation. And what's so great about this chaos program, the XAOS program here, is that we can explore these different equations, like z cubed. And I'll just briefly zoom you in. Remember how everything bifurcated in the z-squared Mandelbrot set? Well, here we find a similar behavior, but different. So now we find trifurcation, which is not an official word, but I think you know what it means. It's branching in thirds. And so we have 3 arms that are coming together, turning into 9 arms, and then 27 arms, and 81 arms. And this math is now experimental. You don't have to trust me for this. You can actually zoom in and count. And everywhere I've ever gone in this thing, it always behaves this way. And there are ways actually of mathematically proving it. But what's fun for kids is that they can discover these rules themselves and figure out how these magical creatures behave because they follow very simple and easily graspable rules. So anywhere I go in this object, it'll follow the same behavior, but the styles will be very different. Notice it looks similar to the z-squared Mandelbrot set with the bulbs on the side and things like that. But here we have trifurcation again. And it always converges around a little copy of the same z-cubed Mandelbrot set down there, which is just an amazing thing. Notice the symmetry in this object. Okay? How many axes of symmetry do we find here? 2. And in the z-squared Mandelbrot set, how many lines of symmetry?
1.
And here's the z to the 4th power. And there's 3 axes of symmetry. So there's an interesting relationship there that's fun to explore. And just to see what do we think the behavior is going to be here as far as branching? Tetraification, something like that. Well, yes, it branches in 4s. So now we have 4 arms branching into 16, into 64, into 256 arms. And again, it's all testable. You can just count these things and see how it works. Really, really, really fun. A couple of more things to point out. You can do that with any arbitrary exponent. It gets tiresome, but computers are really powerful. They can do it. And
5 lines of symmetry.
you know what? There's actually a bug in the program. And this is 1, 2, 3, 4, 5, 6, 7, 8. This is, it says it's to the 6th power, but it's not. I keep meaning to log this as a bug because it's not. Oh, thank you for asking that. I often forget to complete that point. Remember that the points outside the set go to infinity, and the points inside stay finite. But the closer you are to the boundary, to the edge, the longer it takes them to go to infinity, right? And so if you're at a big value, a big number out here, when you square it, it'll get big faster. But when you're right close to the edge, you might have to iterate this equation 1,000 times, or 1,000,000 times, or 1,000,000,000,000 times before it will pass some threshold and escape. Okay, so we can't actually measure how long it takes to get to infinity, but we can see how long does it take to get to the number 2. And then if it gets that big, then it's never coming back. This one, the Mandelbrot set family, they're interesting. Let me change colors a little bit. But so the colors reflect how quickly those points go to infinity. And the closer you are to the edge, the slower it goes to infinity. But these fractals are interesting because you can zoom into them forever, as we've seen, but you cannot zoom out of them forever, because when you get big numbers, then you're outside the Mandelbrot set. So all this area here is not part of this fractal. Boom, it vanishes. There are some fractals, however, that go to infinity in both directions. So this is an example of one of those. You can zoom into this forever. This is called the Newton fractal, and it was invented or discovered by Isaac Newton about 300 years ago. Unfortunately, he didn't have computers, so he couldn't probably appreciate how beautiful his equations were, although he was really, really smart, so he might have had some idea. But this one is perfectly self-similar, so you're never going to find new detail inside here. It's always just matching up, but it's very interesting. But what's fun about this fractal is that you can zoom both in and out. and it never ends in either direction. So it's not just infinitely small, it's also infinitely large. We're getting back to the starting point. Here's where we started, and now it just keeps going.
Did he know about complex numbers?
That's a good question. I'm pretty sure he did. I'm pretty sure he did. No? Really? I don't know. I guess not. But here's what's cool about it, that you actually don't need to know about complex numbers to know about the Mandelbrot set. You can do a purely geometric derivation of it because you can look at it in polar coordinates. And what it means to square a number in two-dimensional polar coordinates is just double the angle and square the radius. And you can create the Mandelbrot set fractal that way without even worrying about what a complex number means.
Sorry, did you answer what determines the color?
Yes, I thought I did. We call it an escape velocity algorithm, and it maps on to how quickly the points diverge.
Right, but the speed determines color?
I get to choose the colors, right? I'm randomly selecting different color palettes, but they map on to...
Concentration of points.
No, it maps on to... Well, let me find a good color map here.
Set an arbitrary, like,
There's a register. Yeah, there's a register or a scale where it's counting iterations, and it basically asks for every point, how many times does it take to pass this threshold? And what's nice about the colors is that every point in space that has the same color has the same mathematical behavior. So you can see these little contour lines here. Any point in this contour and this contour and this contour, they all take the same number of iterations to escape and go to infinity, right? And as you get closer to the thing, it takes more, but it's very useful informationally. You can see, especially in the Mandelbrot set, you can say that something that has the same color, everything that's the same shade of pink in this image has the same number of iterations before it escapes.
Has anyone invented the higher powers? Like this is two-dimensional.
Oh yeah, there are multi-dimensional fractals. There's a whole family of. This is actually the Mandelbrot set. Oh boy, I'm glad you asked that. Okay. This is just a two-dimensional slice of a four-dimensional hypercomplex Mandelbrot set, and it's very hard to visualize and it's very slow to calculate. It takes 16 times as long to square hypercomplex numbers. But you can do it, and you end up with, the problem is they're very hard to visualize. So you can make three-dimensional cross-sections of the 4D thing, but you can't really appreciate the complexity. They all kind of look messy. If you can animate that and move through them, you can slice through it and stuff. It's a very intriguing thing. I'm waiting for computers to get a little bit faster before I start doing that. Now, I'm really, really grateful for all of your attention and patience. It's hard to sit still for this long, and we're just getting close to wrapping up and taking questions. I have a couple more art projects and things to show you, but I want to show you a few more mathematical fractals that are really, really fascinating. First of all, this program just comes with all these different formulas, and I love this one because this one models turbulent fluid flow. And we find turbulence happening at all scales, like the surface of Jupiter, your bathtub, a soap bubble. And this fractal is just a really fun one to play with. So there's many, many different fractals to explore in this program. But remember how I keep insisting that the Mandelbrot set is an abstract object, right? It's not a real thing. It's just made of math. And that is true, but it does connect to the natural world. And I want to show you an example of how that works, because it's really, really intriguing. So let me jump out to this fractal. Now, some of these fractal formulas are made by mathematical explorers who are just playing with their computers, seeing what happens, trying to make pretty pictures. And that's where the artistry of fractals comes in, right? Creating new formulas, exploring the parameter space in these formulas, finding the really beautiful places. And then when you find a really beautiful place, then you color it, you do the painting to make it extra beautiful, and then you print it. Or make a movie out of it. But some fractals come from equations that are not just made up out of thin air. Some fractals come from science. Okay, so here is a fractal that comes from the domain of physics, and in particular magnetism. And I love this example. So there's an equation that describes the way that metals become magnetic or lose their magnetism. And they don't do so in a simple linear fashion. Instead, they do so in a complex, nonlinear fractal fashion where little pieces get magnetized and then it spreads and it magnetizes other parts. They call it percolation. And when you take the equation that describes magnetic percolation and you iterate it like this in a computer, you get these very interesting fractals that have this wonderful property that as you zoom in, look what we find. Amazingly, we find little Mandelbrot set copies in this thing. And this is not just a made-up formula. It's a real-world formula. That's the amazing thing about this. Now, the structure around it is very different. In the Mandelbrot set, there are no connected closed loops like this. So visually, it's a very different material. And yet, everywhere you go in this object, you'll find little Mandelbrot set replicas at the connector points. It's full of them. And this is not the only fractal or the only formula that generates these fractals. Yeah, there's actually an artifact here. You can see the neck. Whoa, hold on. There we go. So the way that this computer program can be so blindingly fast is it takes a few shortcuts here and there. And sometimes it makes a little mistake. But you see these beautiful bubbles. You never see that appearance in the Mandelbrot set quite like that. There's other equations. For example, in ecology, in modeling population dynamics, in a predator-prey relationship, if you're studying the number of coyotes and rabbits, for example, they fluctuate and they oscillate, and it's dependent on the starting conditions very closely, and there's a feedback loop. You keep doing the thing over and over again. Out of that equation comes the Mandelbrot set. It's called the Verhulst equation. And they're finding it in the stock market too, although I don't quite understand how it relates to, but it's this feedback thing where you're looking at nonlinear functions and feeding them back into themselves. And what mathematicians talk about, they use a word called robustness. And what it means is that your system doesn't have to be exactly like the Mandelbrot set equation. The Mandelbrot set is a very powerful force. And if your mathematics just closely approximate the z-squared nonlinear behavior, then you'll get Mandelbrot sets coming out of it. And so there's lots of systems that approximate it reasonably closely. And so they like to say, the people who really study the theoretics of this, that the Mandelbrot set is a universal function of mathematics. It's a universal constant, if you will, very much like the number pi or the number e, which are these numbers that show up in all kinds of different systems. The Mandelbrot set, likewise, is this amazing thing that just shows up in unexpected places in seemingly unrelated studies and systems. So, well, DNA is itself a fractal. If you know how DNA works, it's like back in the days when telephones had cords on them. The cords would tangle and twist, right? And basically, DNA is a supercoiled structure. So it's under tension and it twists, and then it forms a bigger twist. And then that bigger piece of DNA twists again. That's called supercoiling. And then that twists again, and that structure twists again. And eventually, those form the chromosomes. So DNA is itself a great example of a fractal.
Equations, all algebraic equations be made to have a visual component?
Not like this. In order for it to behave like a fractal, it has to have an expanding nonlinearity to it. Basically, that's what the z squared, z cubed thing is. Just z equals 5z plus 3 is a linear equation. It won't generate fractals. Z equals sine of z will. And that's because the sine wave function has little pieces of it that approximate little parabolas. They're close enough to the z squared shape over a certain range that they form really beautiful fractals. But no, not all fractals. Most fractals will. Here's what the z squared, the sine z fractal looks like. I just want to end with one last really exciting thing, and then we can get all informal and answer questions or eat snacks or whatever if there's any left. One of the things that we're up to with the Fractal Foundation is changing the culture, right? We have this opportunity to inspire people with this brand new exciting discovery that mathematics is fun, it's beautiful, and it's exciting. And computers are what let us appreciate that. But people care about it not just because they're pretty pictures, but because of all the relationships I've talked about with nature. This is so incredibly important. We need to foster a culture that values math and science education. We urgently, desperately need this. I don't want to be a doomsayer, but we're falling farther and farther behind the rest of the world in terms of math and science performance. And it's not because our students aren't as smart as anybody else in the world. It's because our culture values sports heroes and movie stars and things like that. We have enough of those. We're out to create science heroes, okay? And to do that, we are engaged in a project right now in Albuquerque called the Albuquerque Fractal Challenge. And this is not a real picture yet. This is a mock-up that helped me secure some funding from the Albuquerque Community the Urban Enhancement Trust Fund. Gave us a grant to run this program. And over the last year, I've been going out teaching kids how to make fractals and giving them the software. Yeah?
What resolution are you going to print that at?
300 DPI. Because computers rock. All right, and because we want to show off the dazzling beauty of fractals. We don't want to print it blurry like a billboard. So what we've done is taught kids how to make fractals, given them the software, and then invited them to submit their favorite fractal to our challenge. So a few weeks ago, we convened a panel of distinguished judges from the arts and science and math communities and selected the winning fractals. And I've got a poster display up here that you can see the winning fractals afterwards on your way out. These are made by students from 5th grade up through 10th grade using the beauty of mathematics. These are all the pictures of algebra, and they are stunning. What the kids have come up with is really impressive. So what we're going to do is reproduce them on the sides of buildings, and we don't have quite enough money yet to print this size. We've got enough for 1,200 square feet of fractals so far, which is big. But we're working on raising money to fractal as much as we can. And we would love to spread this program into Santa Fe. Just eager to do it. So hopefully we can start putting fractals out here, getting the kids in Santa Fe excited about these same things. But this is such an innovative and dramatic program. No other city in the world has a public art program that is using mathematics, using student-made art like this with computers, that not only will everybody in New Mexico see these things, but everybody all over the world is going to be noticing this because it's going to get a huge amount of press. So what we're out to do is make science heroes, little math stars, people who transform themselves from being geeks because they like exploring fractals to being the heroes that all their classmates say, wow, I want to learn to make fractals too. Can you show me the equation for that? And we're working on video games. We're working on little applications where you can create fractals on your cell phone and then email the formula to somebody else's cell phone so they can generate the fractal on their end, making it fun and exciting and beautiful. So that's what we are up to at the Fractal Foundation. Learn more at fractalfoundation.org. Check out one of our First Friday Fractal shows sometime. And thank you so much for your attention.